yell at me. Okay. So yeah, this week we're talking about direct products, and products are something that we probably could have talked about a lot earlier. In fact, when we were talking about, when Ali and I were talking about making test one, I was like, why don't we make them, show that the direct product of groups is a group? And he's like, nah, we already made them show that something is a group. So we didn't do it that way. But finally, I've mentioned a couple of times now that there is this group of order 4 that we keep running up against, where every element, every non-identity element of the group has order 2, right? So it's not cyclic, but it's a group of order 4. And we've seen it a couple of times in a couple of different ways. In particular, at one point we saw it manifest as U12, I think, right? When the very first time when we were talking about the group of units of Zn, and we were computing the orders of thing, U12 came up, and that was an example. So in particular, today we'll be in this nice position where we actually I can show you what that thing is. Like, U12 is not how you should think about it. There is a much, much nicer way of realizing it, okay, and seeing it. So we're talking about direct products. And again, if you've done this in linear algebra, for example, and you've talked about the Cartesian product of vector spaces, it's the exact same sort of thing. So anywhere where you've kind of seen a Cartesian product, even of sets, right? Like basically, this is what we're going to do, just to give you a heads up. We're going to take the product of sets, like the Cartesian of product of sets, and then we're going to figure out how do we put a natural group structure on that space. Okay, so that's what our goal is. And the naive thing ends up working, which is really nice because that's not always true in group theory, right? We've kind of learned that the hard way. So we're going to define a finite product of sets, but in fact, you don't need it. You can do infinite if you want. So let's start out by saying let G1, through Gn be a finite collection of groups. Okay, and again, it's understood, even though I'm not going to write down what each of their group operations is, it's understood they could have different group operations, right? Some of these might be the same group, some of them might be different, but there are going to be implicit group operations here. We define the product group, I guess we'll say direct product, the external direct product. And next week, we'll talk about an internal direct product, but it's pretty much the same thing. Okay, and the way that we write this down, so we have a couple of ways. So kind of the classic way, if you kind of want to write it all out, is you can do this. Right, we use this plus sign with a circle around it, right? So this is just notation. I'm going to tell you what this actually means in a second, but this is how we indicate it. Alternatively, what you can do is just like sums or products or whatever the case might be, you can use like a big O plus I equals 1. Oh, no, I equals 1 to N GI, like that. Okay. And what this is, as this thing, which is the Cartesian product Okay, so what we're saying is the underlying set here is just G1 times G2 ... times Gn. Okay, that's the underlying set with the group operation that's just done component-wise. With component-wise operations, okay? And so what I mean by that is if you have G1 through Gn and H1 through Hn in the Cartesian product, right? Then you're going to define the product of these two elements G1 ... Gn times H1 ... Hn is, well, you're going to multiply these two together in component 1, these things together in component n, like that. right? So that's what we're saying. You're doing it component-wise. You've taken all these groups and you've kind of smushed them together, but in a way that they never see one another, right? Whatever group one is, right, only ever sees multiplication in group one. It doesn't interact with the other groups at all. Everything that has to do with group one occurs in the first component of this n tuple. Whatever has to do with component two is in the nth component of the n, or the second component of the n tuple, and so on and so forth. So even though we formally have kind of put these things together, they really don't interact with one another. And this is very different than something, if you take a more advanced group theory course, you eventually learn about something called the semi-direct product. And in that case, they interact with each other. But here, yeah, it's just component-wise, right? And again, if you've done any sort of linear algebra, like the advanced linear algebra, where you take the direct product of groups or the direct sum of the direct product or direct sum of vector spaces, you know how you add vector spaces, just component by component, right? And it's the exact same thing here. Okay, so nothing sort of crazy there. So are there any questions about this? Because notationally, it can be a little bit heavy. And, I'm about to state formally, like, this is obviously a group, quote unquote, obviously. But if you have any questions about notation, just ask them now so that we can be really sure that we're all on the same page. Okay, it's okay. So we're just going to smush them together, right? And now I'm going to say that this is obviously a group, and you might be, upset by that. This is a group, right? So the identity element is just the identity element from each of the component groups. So the identity element is EG1 through EGN, right? Since if we act that EG1 on any element, again, you're just going to do multiplication component-wise, right? And because the identity element in each component just doesn't do anything when you multiply it, yeah, it preserves the structure, right? So again, if you ignore that sort of middle thing and you look at the very beginning and very last line, so you look at this and you look at this, yeah, this element, this EG1 through EGN doesn't do anything when you multiply it, right? It's the same. And inverses, again, really does what you want it to do. So the inverse of this n tuple is just the n tuple of inverses. Right? So to find the inverse of that n tuple, you just take the inverse of each of its components. This works because precisely if you do G1 inverse, Gn inverse, and again, hopefully you're seeing like, oh yeah, this is just, if you do it on every component, it's definitely going to be true overall, right? So that gives you G1 inverse G1, Gn inverse Gn. That gives us the identity in G1, the identity in Gn, and so on and so forth, right? So yeah, this thing does what an inverse should do because we recognize this component on the left as being the inverse in the direct sum, or the direct product rather. And so yeah, so this is the inverse. And then of course, we only need one other thing, which is associativity. But again, you're associative in each component. So you're certainly associative overall, right? So finally, associativity, right? Like we don't want to write it all out. Associativity follows from associativity in each component. Okay, so this thing is definitely a group. It's a little bit cumbersome. A nice thing that is worth mentioning. So again, I kind of wrote above and mentioned it as I was writing it out, but I started by assuming that we had this G1 through Gn, which was a finite collection of groups. But in practice, this definition does not require a finite collection of groups. You could actually do it for an infinite collection of groups, okay? So I'm just going to zoom up a bit so that we can kind of look at the definition. So we could have done, let's say, countable infinity. It's kind of the easiest one to conceive of. If I'd said let G1 ... or GI in the natural numbers be an infinite, countably infinite collection of groups, we can take their direct product in exactly the same way. The only kind of problem that you get here, it's not even a problem, it's just kind of a notational issue, is that when you write out one of those elements, it actually is this like infinite long n tuple, i.e. it's basically a sequence, right? So you kind of have to deal with the fact that you have this infinite long vector and you have to figure out how to play with it, but that's not a problem. You can even do this for arbitrary collections of groups. So you don't even have to be countably infinite. You could be like, you could have as many groups as there are real numbers, and there's a way of taking their product. That starts to get a little bit tricky. Like we really need to involve functions in order to make sense of that, but there absolutely is a way of doing it. And if you know how to do that at the set level, then you know how to do it at the group level. Okay, so there's a way of doing that with sets. And if you've seen that before in 102 or wherever in your travels, then the way that you define the group is exactly just by doing it component-wise. Okay, now that's not something we're going to worry about in this class, but if you want to mess around with it and try it out a bit, it's fun. And in particular, some of you might have heard of like Hilbert's Hotel, for example, and this is how you can do some like Hilbert Hotel things. It's a very nice, cool little example of something you can do. Okay. So let's do a little example. Let's just smush together some groups. I actually had an example that I was going to push until a little bit later. I guess, you know what, we could just do a small one and just write everything out. So let's say example. Write out the elements of, I'm going to regret writing this, of S3 cross Z2, right? And the reason why I'm going to regret this is this thing evidently has, or sorry, I should write it with the plus. This thing evidently has 12 elements, right? S3 has 6 things in it, Z2 has 2 things in it. And we just know that, the Cartesian product is the cardinality of the product is the product of the cardinalities, right? At the set level. And again, we're saying as a group, this is just the Cartesian product of these 2 things. We use the little plus sign to indicate that we're not thinking about it as a set, but we're thinking about it with this natural group structure that we just defined here, right? That's the difference between writing the times symbol for the Cartesian product and this little plus symbol here. Okay, so I'm just going to write them all out. And then maybe we could even do a computation or so. So let's see. We will get the identity element permutation in 0, right? We'll get the identity permutation in 1. Then let's do the transpositions in 0. And again, you don't need to wait for me if you can see what the answer is. It's a little bit repetitive because there's 12 elements. But look, I'm already done half. 2, 3, 0. 2, 3, 1. Right? And again, we're just kind of formally 1, 2, 3, just kind of formally writing them beside each other, right? There's nothing kind of crazy here. Am I going to fit this? 1, 3, 2. Oh yeah, I got it. Oh, just barely. 1, 3, 2, 1, like that. Okay. There's all the 12 elements. And then if you wanted to actually do here, let's do a product of these things. Just, the example doesn't ask us to do it, but while we're here, let's do one. So if I did something like, let's do something 1, 3, 1 times 1, 3, 2, 1, right? So according to our definition of how this direct product should work, this is going to be 1, 3, 1, 3, 2, and then 1 plus 1. And we can work out what those are. I shouldn't have done a S3 because now I actually have to figure out what this is. 1 maps to 3 maps to 1. So this is, I think, just 2, 3, 0. That look right? Somebody double check my product of, permutations, but hopefully that's right. Right, and you can see that's not tricky, right? We know how to multiply things in S3. We know how to, multiply things in Z2. And so you just do it to each component separately and then smush them back together, right? And here I did a direct product of two elements, two groups. Of course, I could have done more groups as well. Okay. Now, this brings an immediate corollary. Like, I really don't even think that there's anything to prove here. So if G1 through Gn are finite groups, then the order of their direct product is the product of their orders. Right? And the proof of this is trivial. The proof occurs because this is just how cardinalities work at the set level, right? We said it's a group, and we know that the order of the group is the number of elements in the group itself. Well, the underlying set is just the Cartesian product. And this is exactly how this works at the set level. So yeah, there's nothing to prove here. But it is worth noting, right, as this sort of, because we know that the order of the group plays a significant role. For example, we have Lagrange's theorem, right, which says every element of the group must divide the order of the group. So this is kind of a good thing to have explicitly stated, but this shouldn't in any way be a surprising thing. The only thing that you might want to get upset about, and which I would 100% agree with, is this symbol using, the plus sign, because if you're thinking about pluses, but we're calling it products and everything seems to multiply, you might have an objection to that, which I would agree is perfectly fair. Traditionally, when I do these sorts of things, I actually just use the time symbol. But this isn't like an Ali thing. This is legitimately, there are lots of mathematicians who do this. This is a fairly standard set of notation. It can be confusing. Unfortunately, that's life, we kind of do the same thing when we talk about vector spaces as well, right? We'll use this plus sign. We'll talk about the sum of two vector spaces, and the underlying set is their Cartesian product. What are you going to do, right? Unfortunately, that's just the way it works sometimes. Though, I think there is an argument to make that with vector spaces, it is okay, and with groups, it's less so. And the reason for that is a categorical thing. I don't expect any of these words to make sense, but in like vector spaces, right? If you're playing around with vector spaces, products and coproducts are the same thing. At least finite products and finite coproducts are the same thing. So using times versus plus is no problem. But in groups, products and coproducts are different. And in particular, this isn't a coproduct. So, and usually we denote coproducts with a little plus sign. Anyway, whatever. Don't worry about that. That's just me. I had to say it because, I had to get it off my chest, but whatever, who cares? Okay, though it is a coproduct with abelian groups, whatever, it doesn't matter. Okay, so are there any questions so far? Does that make sense? Hopefully it does. Right, like I don't think, and if you're struggling a little bit with this, or maybe you just don't feel super comfortable with it because it's our first time doing it, that's totally okay. But that being said, I don't think that we're doing anything like mind-blowingly difficult, right? Finally, let me show you that group of order 4. If you had to guess what it was, maybe you could. This thing right here is called the Klein-4 group. Okay, and we could write them all. And in particular, right, it's interesting because it's the first group which is not cyclic, right? All groups of order 1 are cyclic, groups of order 2 are cyclic, groups of order 3 are cyclic. Groups, it is the first, it is the smallest order of a group that is not cyclic, right? That's why it has a special name. So we can just write out the elements of these things. Right, so this question doesn't ask us to do anything in particular, but let's just write it out. So as a set, this is 0, 0, 1, 0, 0, 1, 1, 1. Okay, and I had mentioned before, this is precisely that thing that is a group of order 4 is not cyclic. I claim it's not cyclic. It might not be obvious, but it is a group of order 4. It's not cyclic, and the order of every non-identity element is 2. Now, two of those things are related, right? If every non-identity element has order 2, the group can't possibly be cyclic, right? To be cyclic, there would need to be an element of order 4. So let's check it though, right? Like let's just compute the orders of things. So the order of 0, 0, I mean, this is already the identity, right? So that's easy. So that's 1. Okay. So if I take 1, 0, and I add it to itself, what do I get? So I'm going to get 1 plus 1, 0. Oh yeah, that's 0, 0, right? So that tells us that the order of 1, 0 is 2. All right. And you can imagine the same thing is true for 0, 1. Hopefully I don't have to write that one down. But it's the exact same story, right? If you add it to itself, you get 0 in one spot, 1 plus 1, which is 0 in the other spot. That's also equal to 2. And then finally, the same thing with 1, 1, right? If you add it to itself, you're going to get 0 in both slots. So here you go. Here's a group of order 4, and the 3 non-identity elements have order 2. And we've seen something like that, right? So we could say compare this to U12, which remember is 1, 5, 7, and 11. And we also found way back in the day, you might need to double check this calculation. The order of 1 is 1. The order of 5 squared is 25, which is just 1. The order of 7 squared is 49, which is 1. And 11 squared, oh, sorry, is 2. Why am I writing 1 here? Get caught up there. And 11 squared is 121, which is, again, of course, congruent to 1. So the order of all of these things is equal to 2. And if we explicitly want to write down an isomorphism, so we could say define phi from U12 to Z2 plus Z2, okay? And yeah, let's just do kind of the obvious thing. Let's map 1 to 0, 0. That has to be true for it to be a homomorphism, right? And then let's map 5 to 0, 1. 7 maps to 1, 0. And 11 maps to 1, 1. This is a homomorphism. And in fact, it's relatively easy just to check. Certainly, like I said, the only things we really need to check are, phi of 5 times 7 is equal to phi of 35. Now, what is 35? Phi of 11, right? But phi of 5 plus phi of 7 is equal to 0, 1 plus 1, 0 is equal to 1, 1. And yeah, that's phi of 11. Right, so we've shown that phi of 5 times 7 is equal to phi of 5 plus 7. And you can do this for all of them if you really want, right? 5 times 11 is phi of 55, which is what, 7? I guess I should write. And that is 1, 0. And then if we were to check what phi of 5 plus phi of 11 is, we get 0, 1. Plus 1, 1. And yep, that is 1, 0. Right, and let's just do the last one. So phi of 7 times 11. So that's 77, which is what, 5? So that's 0, 1. And then phi of 7 plus phi of 11 is 1, 0. And yeah, you can see it's going to work. Right, so those are equal as well. And again, the groups are both all commutative. And so we're done, because certainly 1 times anything is going to work. So we only had to kind of check the pairwise multiplications, and we get that they all work. This is evidently injective. It's evidently surjective. It's a homomorphism. So phi is an isomorphism. Okay. And, we saw the exact same thing on Thursday, I'm pretty sure, when what did we do? We had this exercise in the worksheet that said something like compute G mod H, compute G mod K, are they isomorphic? And we got in one case that G mod H was Z4, and that G mod K, if you remember from Thursday, G mod K was, again, this group of order 4. It did have the right size, but every non-identity element had order 2. That was the Klein 4 group in disguise, right? And it was very easy. It would have been very straightforward for us at the time to have defined the isomorphism, but just unfortunately, we didn't know what the Klein 4 group was. So this, as a general rule, of course, you could use U12 to represent your Klein 4 group if you want, but the rest of the world, if you talk about the Klein 4 group, recognizes this as Z2 plus Z2, okay? So this is this nice thing to keep in mind here. You know, that's the Klein 4 group. In fact, we don't yet, I mean, we could prove this, but I don't think we have. Z4 and Z2 plus Z2 are the only groups of order 4. Okay, and if you really want to prove this, it's relatively easy. It's kind of a pain, but it is easy. And it's basically just write out the Cayley tables, right? The multiplication tables for groups of order 4. And what you'll see is that there's only like 4 of them that you could possibly write down. 3 of them are isomorphic to Z4, and the other one is the Klein 4 group. So you can prove, if you're just willing to brute force it, you can write down all of the possible groups. 3 of them are isomorphic to Z4. 1 of them is isomorphic to Z2 plus Z2, and that's all of them. Okay, so that, in some sense, I think that's worthwhile. Let's write that down explicitly. So let's say comment Z4 and Z2 plus Z2 are the only groups of order 4. Okay. And that's nice. And really, again, that really is a byproduct of the fact that they're so, like 4 is a small number. There's this cool thing. I don't know if any of you have stumbled upon this. Generally, groups that are powers of 2 are a nightmare. Z4 is nice, but I think 10 to the 20, is it 10 to the 24, which is the nightmare one? Let me see. Groups of order 10 to 24. I think it's 10 to the 24 that's. Yeah, oh, here's a nice statement. If you write down all the groups whose order is less than 2000, okay? So think about it, that's a lot of groups, right? Some of them are abelian, some of them are non-abelian, whatever the case is. If you write down all the groups of order less than or equal to 2000, 99% of them have order 1024. Like 1024 is such a crazy number in group theory for whatever reason that 99% of all of the groups of order less than or equal to 2000 are of order 1024, right? Just as like a crazy thing to little tidbit in fact to like blow your mind. Okay. Good. Oh, somebody actually has the number here. Let me copy it down. Okay, I'm going to put it in the chat so I don't have to. That's how many groups of order 1024 are. There are. What is that number? What's the order of that number? 49 million. So there's about 50 million groups of order 1024. Is it 49 billion? Oh, you're right. Sorry, it's 49. Yeah, it's 49 billion. Thank you, Harvin. So it's so much worse than what I said, right? There are 49 billion groups of order 1024. Hyun, this is an interesting question because I guess what you could actually do is you could set up a computer and say, compute all the Cayley tables. And then if you were really good, you could do something like figure out which one of these ones are isomorphic just using a computer. The reality is that I don't know actually how they figured this out. This goes into a level of discrete groups theory that is beyond me. I don't know. I legitimately, this is a level of group theory that for most mathematicians, you know, because it's just this interesting tidbit that you could explain to like any third year math student. But to be honest, I don't know. Apparently the number, from what I'm reading here, the number of groups of order 2048. So Paula, this is kind of related to your question. The groups of order 2048 are unknown, but it does exceed this number. It is known to exceed this. And what is that? Oh man, we need to put commas in this, right? 992.116. So there's the millions. There's the billions. 1.7 quadrillion. Is that, did I parse that correctly? Yeah, that's crazy, right? So there's something about, I don't think it's that it's 2 to the 10 poly, it's the powers of 2. There's something about the powers of 2 that just, if you like plot the number of groups of a particular size on a graph, and in fact, you can probably, if you Google this, I think you can actually find it. If you plot the groups and you say like, let the x-axis be the order of the group and the y-axis be the number of groups that hit that order, I think you do see a spike at every power of 2, right? So there's something about powers of 2 that do this, but this goes into a level of group theory that, like I said, even I'm not familiar with. Yeah, there's like, one of the great theorems of group theory is that they basically have a complete classification of finite simple groups, right? And like, that is a major theorem that took, you know, dozens of mathematicians a couple hundred years to do. So the depth of classifying finite groups is to some extent, well, not really is anymore, but was for a long period of time, a deep and extensive field of research, right? So that wasn't my area of research. Again, I kind of work with continuous groups, right? Groups of order infinity. So it's not my thing. I think, I'm not certain if Ali would know either, actually, to be honest, but he would have a better chance of knowing because he is an algebraist at the end of the day, right? Like, I'm a geometer, so my exposure to groups is usually through geometry, but he's an algebraist. So I'll ask him at some point and see if he knows. And then I might tell you on Thursday or maybe next Monday if I get an answer from him. Or maybe let me do some research and I'll look into it and see if I can come up with a good example. There's things that you can say kind of like related to the C-love theorems, which again, we don't do in this class, but there's a lot of things you can do where you take the prime factorization of the order of the group. So you take the order of the group, you write it as a product of primes, and then those primes correspond to certain subgroups. And then you can use those subgroups, I think, to try and rebuild the group. I don't remember exactly how this goes. It's been a while since I had to do this, but there's some stuff you can do there. Anyway, that's just kind of a cool and interesting thing if any of you wanted to like play around with that, do some kind of personal, just research on that. Okay, so I want to try and get this result out of the way maybe before we take a break here. And it's going to state as the following. This is, I think, going to be a little bit scary when I write it, but it's not scary at all. Okay, so suppose that G1 through Gn is a finite collection of groups. And sigma is an element of Sn. Okay, and importantly, this is the same n, okay? So this n that is enumerating the number of groups is the same as this n here, okay? That's not a typo, that is very much on purpose. Then this is true. Okay, and it might take you a second to parse through that, but I don't think it's too terrible. What this basically says, maybe let me write this as a comment. It's that if you just reorder the groups in the direct product, that is going to be isomorphic, right? So any reordering of the groups in the direct product is just isomorphic to each other. So reordering the groups results in an isomorphic group. Okay, and so for example, if we have something like G1, G2, G3, G4, and let's say sigma is 1, 3, 2, 4, then what I'm saying, what the theorem says, if we actually were to apply it with n is equal to 4 and this particular value of sigma, we would say that G1 plus G2 plus G3 plus G4 is isomorphic to, and you don't, if you can see what I'm writing here, you can just go straight to the final step. I'm going to include this intermediate step just to kind of spell out what's happening here. So G sigma 1, G sigma 2, G sigma 3, G sigma 4, like that. But we don't have to leave it like sigma 1, sigma 2, sigma 3, sigma 4. We can actually compute explicitly what this is, because we know sigma 1 is equal to 3, right? So this is equal to G3. Sigma 2 is equal to 4, right? That's how a permutation works, right? Okay, sigma 3 is equal to 1. And sigma 4 is equal to 2. Right? So you can see what the permutation does. The permutation switches 1 and 3, and that's exactly what we did with the groups as well, right? We just switch where G1 and G3 occur in the product, and it also flips 2 and 4, right? So it also just flips where 2 and 4 occur in the product. And so what this theorem is saying is that if I do this rearrangement, I get something which is isomorphic. It's strictly speaking, it's a different group, right? Because their underlying sets aren't even the same. Their underlying sets are in bijection, but their underlying sets aren't the same. So this is a nice little theorem just to convince ourselves that, yes, this should be obviously true. It shouldn't matter if I change the order of the groups in my direct product. I will result in a different group, but I'm just get something that's isomorphic, right? And again, the groups aren't interacting, right? And because the groups aren't interacting, who cares where they show up is basically the idea. They just play with each other, right? Or they play with themselves. They don't interact with their neighbors at all. And so if you just formally move who's standing where, it doesn't matter, right? You get something that is fundamentally the same group. And so the proof of this is just do exactly what you think you should do, right? Which is to define this map, right? We want to show that these things are isomorphic, so we actually have to define an isomorphism. And the way that this is going to work is that you're going to give me an n tuple, and I'm just going to scramble that n tuple in exactly the same way that sigma does, right? Okay, and from our example above, maybe let me just kind of put this on the side here. If we kind of want to use our concrete example of n equals 4 above, what I'm basically saying is that phi of G1, G2, G3, G4 is equal to G3, G4, G1, G2, right? So i.e. you just scramble them in exactly the same order as what you did above, right? Does that make sense? Right, so I'm just reordering the n tuple. That's all I'm doing. And I claim like this is obviously a bijection, and it's also obviously a homomorphism. And mean, like, you know, we should do better than that. Now, if you want to, you can actually prove that this map is bijective, right? You can prove it's injective. You can prove that it's a homomorphism. You can prove that it's surjective. I'm going to say my favorite way of proving that things are bijections is defining an inverse. So what I'm just going to do is I'm going to define phi inverse, which takes G1 through Gn and maps it to G sigma inverse of 1, G sigma inverse of n, right? Because you know sigma has an inverse. Every element of Sn does because it's a group. And if you compute phi of phi inverse, yeah, you're going to get G sigma inverse of 1, G sigma inverse of n, which is G1 through Gn. Okay, therefore phi is injective, right? That's actually what I did here, right? Is I proved that phi was, or sorry, this is actually surjectivity, so phi is surjective, and then the opposite direction. So I think this is easier than proving injectivity and surjectivity, but you might disagree. And if you disagree, that's fine. you can redo the proof and prove injectivity and surjectivity your way. Right? So I also have a left inverse. That means I'm injective. So phi is bijective. So thus phi is bijective. And moreover, it's a homomorphism because, and now we kind of see the pain in the butt of working with these things, right? Is that notationally, this is a real pain. G1, H1, GN, HN. Okay, and that is going to be G sigma 1, H sigma 1. Right, and the reason for that is, again, all we're doing is rearranging. So G sigma N, H sigma N. Hopefully my notation is still readable because I'm having to draw these things pretty small. H sigma 1, H sigma N, and that's phi. G1, Gn, phi, H1, Hn, right? So it is a bijective homomorphism, therefore it's an isomorphism, and we're done. Okay. So again, hopefully that's not too bothersome. Basically, the claim is, right, like I said, you can just reorder the terms of a direct product however you like, and you get something that's isomorphic. Strictly different, but isomorphic. Okay? Okay, so I think that's probably our natural break time because it's just after 2 o'clock. Let's take a 10-minute break. We'll come back, and then I will define for you the canonical maps. And we'll do a slightly harder example, something cool that I really like, I think is a fun thing. And then we'll finish off the class with some statement about quotient groups and products. But again, it like, don't freak out because I know quotient groups are tough, but they do exactly what you think they should do, right? Like it's not tricky at all. Okay, everyone, so 10 minutes, it's 2:03 by my watch. So let's come back at 2:13 and we'll finish it off. And of course, don't hesitate, throw any questions that you have in the chat and I will answer them when I get a second, but before we get back. Okay, everyone, 10 minutes. See you soon. And again, yeah, Harvard makes a nice observation too, because I posted the OEIS thing for the sizes of the subgroups of those orders, and Harvard kind of points out, yeah, anything that's close to pure power of 2 also has a large number of groups. And exactly my understanding is that that is related to this 2 to the n, right? When your prime factorization has a 2 to the n in it, basically it just causes the number of possibilities to explode. Another cool thing is, I don't know how many of you have ever played with the OEIS before. The OEIS is pretty cool as long as you know what you're looking for. It's the online encyclopedia of integer sequences, right? So it keeps track of sequences of integers. And there are some times when you're like doing research and you're like, oh man, I think there's a pattern here. I wonder if it's related to something. And then you can go and you can search that pattern in the OEIS and see what it's related to. And then that can give you some interesting links to, you know, fields that you didn't think about. So it's an interesting little encyclopedia. It can be boring because there's a lot of sequences in there which are kind of generic and dumb. But in fact, I'm pretty sure if you go and you like do a stack exchange, I'm pretty sure there's like a mass stack exchange of what are the coolest sequences in the Encyclopedia of integer sequences, and it'll give you a bunch of cool math there. If that's, again, a nice little rabbit hole you can go down. Okay, so I said we would come back and I would talk about the canonical maps. Okay, and does anyone know what the word canonical means? So you'll often hear mathematicians say this word, but we often don't define it. And so some people don't know what canonical means, but does anyone know what canonical means? Just out of curiosity. Classic is close. It's similar, but there are some classic things which are not canonical, right? So for example, the standard basis is a classic basis, but it is not a canonical basis. You know what I mean? Like if you're looking at, well, okay, so for example, if you look at R2, right? Like let's forget group theory for a second. And if you look at R2, right, as a vector space, we know that like this is certainly a natural basis to choose, right? But it's not a canonical basis. So we have to be a little bit careful about that. So what canonical means is that you don't have to make a choice. You don't have to make any choices. Okay, because often, for example, when you're doing things like isomorphisms, you have to make a decision, right? Think about when you're trying to show that, for example, two vector spaces are isomorphic. What do you usually do? You fix a basis for the first vector space, you fix a basis for the second vector space, and then you map one basis to another, right? That isomorphism depended on your choice of basis, right? You had to make a choice for which basis you were going to take for the first space and which basis you were going to take for the second space, right? There were choices involved in what you did. Canonical things must be choice independent. So in some sense, canonical can be thought of as not quite natural, but as being intrinsic. Does that make sense? Like it's intrinsic to the object that you're thinking about because you don't have to make any choices at all. Okay, so these are the canonical maps. So I'm going to define them for a product of two things, but obviously you can generalize this as much as you want, but let's just kind of focus on what's going on when we multiply two maps or two groups. So let's say let G and H be two groups. And let's let G plus H be their product, right? Okay, so we have the canonical maps, which are called the projection maps. Okay, so we often might call this like pi G, which maps G plus H onto G, and it will take GH onto G. And then same thing, there's pi H, which takes G plus H onto H, G comma H onto G, or sorry, onto H. Right? Does that make sense? You notice how I didn't make a choice there, right? I didn't have to like decide what these maps would do. They're just canonical, right? They just exist. They're intrinsic to the definition of the direct product. Okay, let me scroll up very, very quickly. So for example, you remember when I was showing that U12 is isomorphic to Z2 plus Z2? Notice I made a choice here, right? I had to decide that 5 mapped to 0, 1, 7 mapped to 1, 0, and 11 mapped to 1, 1. If I can actually change those around, right? And I could have mapped 5 to 1, 1, for example, and 7 to something else, and still have gotten an isomorphism. When I did this isomorphism, I had to make a choice as to what things were going to map to what things, okay? So that isomorphism up there was not canonical, right? I had to make a choice. These projection maps are canonical, right? There's no choice involved here. If I'm going to map G to G, right, G comma H to G, there's only that's the only thing that I could have done, right? There was no choice involved in defining these maps. Note as well, both of them are homomorphisms. In fact, surjective homomorphisms. Both are surjective homomorphisms. Okay, and this gives us a very kind of nice first result, which is like, let's look at the kernel of one of these things. Okay, so the kernel of pi G, let's say also, the kernel of pi G is what? So this is a collection of all elements GH in G plus H, such that G is equal to the identity, right? That's the same thing as just saying EH, right? Where H is allowed to be anything. And yeah, I mean, this was probably, you probably could have guessed that this was the kernel, right? Just everything in H, this is basically just everything in H is the kernel of pi g. And so what this tells us, by the first isomorphism theorem, we have the g plus h divided by the kernel of pi. Okay, so what is that? That's g plus h divided by e plus h. That's actually really, we could write a plus here if we wanted. And that's going to be isomorphic to the image, but this is clearly surjective. So it's isomorphic to G. So like, let's take a look at this. Right? That's kind of a nice and evident thing. Like that seems like that should be right. If I quotient out by E plus H, like it's like I'm quotienting out by the E on the left-hand side and the H on the second-hand side. So it's like the H's kind of cancel. And again, maybe this is even kind of more evident if we write it using, multiplication. Right? That thing looks like it's this. Right? So it looks like there's like all this cancellation going on. I'm dividing G by 1, so it's just going to be G. I've got H divided by H, so that's just going to be 1. And the thing that's left over is G, right? So that's kind of nice. You can imagine that exactly the same sort of thing happens with H as well, right? So these are the canonical projection maps. Both of them are group homomorphisms. And we've also are going to have the canonical inclusions. So we usually use iota. So this is IOTA, right? Iota. And you can imagine what we're going to do here. So I have to choose an element of H that I'm going to map to. I think the obvious thing to do is the identity. And this will take H to the identity H, right? And again, you really want it to be the identity in order for these to be homomorphisms, right? If you chose, I guess you could actually, no, so these are canonical in the sense that if we want them to be homomorphisms, so you could say like you chose that identity element, right? And so there's a sense in which this is not canonical, but it's canonical if I want these to be homomorphisms. That's the only thing that could be, right? I don't have a choice for the identity element. It has to be that. So there might be some conflict as to whether or not these maps are canonical, but look at what happens. For this to be a homomorphism, because I'm going to have IG of G1, G2. That's going to be equal to G1, G2 times the identity of H, which will be G1 times the identity of H, G2, the identity of H, and that is indeed G1, G2, right? And if you want this to work in general, right? If you want it so that no matter how many of these things that you compose, you're always guaranteed that it is a homomorphism, right? Because here, yes, I use G1 and G2, but it should work if I use G1, G2, G3, G1, G2, G3, G4. The only way for this to work is if I have that identity element in the right-hand side, right? It basically has to be that. So in all fairness, you could make an argument that as a set theoretic map, this is not canonical, but as a group map, it is canonical, whatever. The canonicality, canonicism, whatever the word is, we're not going to be super worried about that. So if you maybe take contention whether this is canonical or not, it's okay. It doesn't matter. We're never going to test you on what's canonical or not, right? So don't worry too much about that. But we have these inclusions. And then note that, what do I want to say? The inclusion and the projection are one-sided inverses of one another, right? But only on one side. Okay, so note that pi G composed with the inclusion of G is the identity map on G. The opposite direction is not true, right? Does the opposite inclusion even make sense? So if we do the projection and then the inclusion, yeah. So the opposite composition is doable, right? You actually could do the opposite composition, but it is not the identity. So if you don't see this, let's actually try it out. So since pi G times the inclusion is going to be pi G of G times the identity in H, but that just gets rid of the identity, and so it just gives me back G, right? So that isn't the inclusion, but the opposite direction is not true, right? But IG composed pi G is not the identity on G cross H, since if I take pi, I guess we have to include IG pi G GH, that's IG of G, that's equal to GEH. And that's not going to be true for every GH, right? Like these two things aren't equal. Right? So this is not the identity. So you do get that iota is a right-sided inverse to pi, and pi is a left-sided inverse to iota. But again, that's not surprising. We knew that pi was surjective, so it does have a right inverse as a set theoretic map, and iota is injective, so it should have a set theoretic left inverse, and both of these just happen to be homomorphisms, which is nice. Okay, does that make sense? So that's a nice thing. I'm going to have to push that example to the end because I actually don't know if we're going to have time for it. I want to get to these things. Are there any questions so far? Is everyone okay? And again, you can imagine, like I said, I only did this for two groups, G and H. But if you wanted to extend this to an arbitrary collection of groups, no problem, right? Or an arbitrary finite product, the projection still does exactly what you think it should do, as does the inclusion. Okay, so there's nothing kind of crazy there. Let me state the following theorem. This is a really nice one because I think that it looks much scarier than it is. So if G1 through Gn are groups, and Ni is normal in Gi for I equals 1 to N, then N1 plus ... plus N, maybe N was a bad choice, but whatever, is normal in G1. Okay, so we have two results here. Basically, the direct product of normal groups stays normal. And then secondly, this is isomorphic to G1 mod N1 plus G2 mod N2, right? Which is, again, kind of that thing I was alluding to above. That it seems as though when you take quotients, they kind of separate nicely like this, right? This is kind of like the best case scenario in terms of what you would expect these quotients to do. And yeah, it turns out to be correct, right? So that's really, really nice. I think that this is a cool little result. And I think the first time that you look at this, you can be like, ooh, like how the hell am I going to prove this? So notably, Ali does prove this in the notes, but Ali's proof is actually unnecessarily long. So he does the proof that N1, that the product of the normal groups is normal. He actually proves that, but it's unnecessary. So what I'm going to do is I'm going to show you the proof. And the proof is very similar to what Ali does in the second part of his book, but it makes redundant the first part, right? So what we're going to do, we're really going to leverage and lean on our good friend, the first isomorphism theorem, right? So let's define a map from phi, yes, which maps from G1 O plus dot 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 O plus Gn onto G1 mod N1 Gn mod Nn. And the way that this is going to do is it's going to be the obvious thing, right? So you're going to take G1 through Gn, and you're going to map it to the coset Gn1 Gnn. Okay. It's very easy to check that this is a homomorphism. Okay, very easy to check. This is a homomorphism. In fact, it's surjective. Maybe let's say that. So check this is a surjective. Is it obvious though? Right? I'm hoping that it is. Basically, look at the map G1 maps to G1 N1. That's our projection map from quotients, right? We said we know that that's a homomorphism, right? The map that takes an element of the group and maps it to its equivalence class, right? We know that that's a homomorphism. And all I did was do that in every component. So yeah, when I string all those together, it is going to be a homomorphism. And if you want, you can kind of check that explicitly. And that map is also surjective. So each of those components is surjective, and therefore the map in its totality is also surjective, right? So basically that's all we're using is just over and over again, the map G to G, or let's say GI to G, GI maps to GI maps NI is a surjective homomorphism. And you know that already. You don't have to prove that. This map is just that, right, in each single component. So the whole thing is evidently a surjective homomorphism. And like I said, you can write it out if you want. And okay, so what's the kernel of this? So the kernel of phi is going to be those n tuples, right, such that the thing on the right-hand side is the identity, right, such that G1N1, GNNN is equal to just N1, NN, right? Because that's the identity in each of these groups individually, and so their product will be the identity in the overall group. But remember, what does this mean? So this basically says that this is the G1 through Gn, such that GINI equals NI for I equals 1 to n. And this is only true if GI is in NI, right? So what we basically have is so by the first isomorphism theorem, we are going to have the G1, the original group, mod its kernel, is isomorphic to its image, but this map was surjective, so its image is everything. All right, and we're done. And again, that proof's actually not very long. The majority of it is me writing ... right, for all the messy products there. So yeah, and I don't think that that's too bad overall. It's just, it looks longer than it is because products are a little bit messy to write down. Okay, any questions about that? That's a nice little thing, I think. Okay. Now, eventually, what ends up being done in the, so I proved this one because I thought it was a nice example of the first isomorphism first isomorphism theorem, and I really wanted to do it for that reason. This one is done in the notes in one form or another. I don't remember if maybe he does it inductively, if he goes straight to it. But yeah, I really like this one just because it is this nice example of first iso. But yeah, I think that there is one thing before I kind of do my really fun example, and hopefully we'll have time for it. There's one more thing that explicitly kind of needs to be said, right? So I'm just really highlighting a quick survey of these results, just related to direct products. The last one I want to touch on, I'm not going to prove this one. The proof isn't terrible though. And it was this one. So if G and H are finite cyclic groups, then G plus H is finite and cyclic. I mean, the fact that it's finite is trivial. The interesting thing here is cyclic. If and only if their orders are coprime. Okay? And of course, you can immediately inductively expand this to as many groups as you want, right? So as long as the orders are all pairwise coprime, that immediately extends. So if G1 through Gn are finite and cyclic, then their product is finite and cyclic if and only if their orders are pairwise coprime. Right? And so what this immediately allows you to do is to like make extremely powerful results about products of cyclic groups. So for example, so what example did I choose? I'm going to choose Z210. Okay, and the reason I chose this is because this is exactly, assuming that I remember how to multiply, right? So 100, let's see, 6 times 35, right? So it's 180 plus 30, so that's 210, right? So this is true by the previous corollary, right? I've taken the direct product of Z2, Z3, Z5, Z7. Those numbers are all prime, so they're definitely pairwise coprime, and that means that their product group is cyclic and has to be the cyclic group of order 210, right? Because the order of the thing on the right-hand side is 210 and is cyclic, so it has to be Z210. But more importantly, I can also then say stronger things because I can combine these in whatever order I like, right? So for example, I could say that this is Z6 plus Z35, right? Those are the same things because Z6 is isomorphic to Z2 plus Z3, Z35 is isomorphic to Z5 plus Z7. Or we could do something like, you know, what do we want here? Let's do Z30 times Z7. Right? Or you could do all sorts of things, right? You could do like Z10 plus Z70. Okay, these are all isomorphic by the previous theorem. And there's a whole bunch you could do, right? There's a bunch of them that I haven't written down because, for example, I could do something like, oh, I could keep the Z2 kind of fully decomposed and then do Z105 here, right? So there's a whole bunch of things that you could do, just every single possible way that you could combine Z2, Z3, Z5, and Z7 to make a group. You now have all of these isomorphisms for free, which you don't have to prove any about. Yeah, thank you, Z21, thank you. Right? So that's super nice. That's super, super nice. And basically, I kept, alluding to this. What you can immediately see, for example, is that if P and Q are primes, that ZPQ is ZP plus ZQ, right? And generally that works for any product of primes. Now you can't take any powers of those primes, right? Because we know, for example, that Z2 plus Z2 is not isomorphic to Z4, right? The Klein-Forer group is not cyclic. So the moment you have powers of primes in your prime factorization, you're in trouble. But if you can factor your number into a distinct product of primes, boom, you're immediately done. And it doesn't have to be primes, right? This corollary at the top of the screen does not say that these numbers have to be primes. It's just the primes are nice because you automatically get it for free. It just says that the numbers that you factor it as have to be pairwise coprime, right? Has to be pairwise coprime. That's all that you need. Okay, so that's kind of a nice little thing that you can do there. Again, as a result of these products, right? You get a ton of isomorphisms for free. So I would suggest that you kind of go through those proofs quickly and just kind of reason to yourself why they work. And in particular, I think that proof, it's really worth even just doing this. Okay, I think it's really worth just explicitly doing that example, right? And just see what you get. In fact, can anyone think of a generator for Z6? So i.e. an element in Z2 plus Z3 that has order 6. Can anyone think of one? Right. So I claim that this thing is Z6, right? So for example, so I claim that Z2 plus Z3 it basically is Z6. Not only is it isomorphic, but it basically is. So what that means is I know that this thing for sure has order 6. So to show that it's cyclic, I need to show that there's an element in here that has order 6, right? So is there an element? What can we obviously think of an element in here that does have order 6? Exactly, 1, 1, which again, in some sense should be obvious. That should be the generator, right? You would expect that that's true. And in fact, we can check 1, 1 does have order 6, right? So claim is that Z2 plus Z3 is generated by 1, 1, okay? And if you've done the readings, you actually know this immediately is gonna work because the order of an element is the least common multiple of the orders of its components. So the first one has order 2 and the second one has order 3, which means overall this thing has order 6. But what we can actually do is step through and I think it's worthwhile to see that this has order 6 and to see what happens. Okay, so let's try it. So if I do 1, 1, I like to write this in multiplicative notation. I think Ali would typically do it in exponential notation. But this is going to be 0, 2, right? 3 times 1, 1 is going to be 1, 0. And look at what happens. 0, 1. 5 times 1, 1 is equal to 1, 2. And then 6 times 1, 1 is in fact 0, 0, right? So this shows that the order of 1, 1 is equal to 6. But if you can see what's happening is that the first element, right, the first one is, right, our goal is to get to the identity. Our goal is to get to 0, 0. The first number keeps alternating between 0 and 1, 0 and 1, 0 and 1. And so we need it to be 0. The second number goes 1, 2, 3, 1, 2, 3, 1, 2, 3. So imagine that you have something that repeats every, jumps between 0 and 1, and then you've got this like triangle sort of face. It's like a clock, but it's triangular, and it goes, 0, 1, 2, 0, 1, 2. And these both start on 1, and you need them to somehow like both arrive at 0, 0 at the same time. It's going to take you 6 multiple, right? That's kind of like, I forget what you would call that, but I think that you would do this sort of like reasoning precisely in high school or maybe even elementary school, right? If you got something, a clock face over here that has only 2 hours and a clock face over here that has 3 hours, they both start at 1 o'clock. How long does it take before both of them show midnight? Well, it takes exactly 6 hours, right? And that's exactly the least common multiple of those two numbers. So it's worth it to actually play around with this and to see why that's true. If you want another example, which is basically the same sort of thing, try something like, we can say something like find the order of, let's say 1, 1, 2, 3 in Z2 plus S3, right? And again, we know that the answer here is going to be 6, right? Because the first element has order 2 and the second element has order 3, and their least common multiple is going to be 6. But like actually write it out, compute this thing 6 times. And what you're going to see is, yeah, both of them hit the identity at separate times. You need them to hit the identity. You need each component to hit the identity at the same time. And that's going to happen at precisely at the least common multiple. And it's going to build up a lot of motivation for how the proof of this thing actually works, right? For how the proof of these theorems actually work, right? It's a very sort of similar process. And it's good to have that intuition because I'll tell you right now, I don't remember these theorems. I just know instinctively that these isomorphisms are true because I have this feeling in my brain, oh, look, they're co-prime. So I can guarantee that there's something which generates the entire group because I know that because they're co-prime, they're not going to end up being the identity at the same time, right? The two components. Does that kind of make sense? Do you kind of like see how that's working? This is what I'm saying. If you haven't actually done one of these computations explicitly, it's worth going through just to kind of build that intuition behind the fact that these things are like different clocks operating on different time spans, and you're trying to get them to say the same time. And that's how it goes. Okay. So I don't think I'm going to get to my final one. If anyone wants to try it though, and actually, you know what, maybe I'll do it first thing Thursday, but I don't think I'm going to have enough time for it. So maybe let me post it as an exercise here. And then I'll do it on Thursday if there's enough interest. So show that if Q is isomorphic to G cross H, then one of G or H is trivial. Okay. So namely, that the rationals are not a direct product. You cannot write them as a direct product of groups non-trivially, right? Like it's basically Q is isomorphic to Q cross the identity or the trivial group. If you're going to do it as a direct product, the rationals are isomorphic to the rationals times the identity. Or I guess I should write plus here again. Okay, so that's what I want you to do. Prove that the rationals cannot be written as a non-trivial direct product. This one's a little bit intense. I would recommend as a hint, I think there's a couple of ways to do it, but here's how I did it. So hint. So look at this. So you've got phi, right? You're told that these are isomorphic. So you've got this map from the rationals to G cross H, and you've got this projection onto the identity. Right? So show that the kernel of, what's the order I want to do this in? So pi G compose phi is trivial. Okay. So basically you're going to take a rational number, you're going to map it to its direct product of decomposition, and then project that down and just pull out the first component, right? So you're saying, suppose that I can write, and of course here I'm kind of saying, suppose G is non-trivial. Look at suppose that you can write the rationals as this direct product, and then you just pull out the first of these elements of the direct product. Show that this map is injective. And then if you show this is injective, you're done. Why are you done if you show that this map is injective? Okay, so I want you to think about that for a little bit. I think this is a good time to maybe pause. Like I said, I think I'll maybe take this one up on Thursday. This is a nice, fun one if you want to do an example that's a little bit more involved. Okay, this is a good one. But otherwise, I think I'm going to call it here. Again, for those of you who haven't filled out your course evaluations yet, please go do that. And yeah, that'll do it for today. And I'll see you all on Thursday in the penultimate class of the term. Thank you. And of course, I'll hang around, right? It's my office hours as well. So if anyone has any questions, I'm going to stick around for a bit. No problem. Thank you. Thank you.